Good afternoon, all. I am Dick Kell, Chairman of the Warren Centre Humanitarian Engineering Hub, and it is my pleasure to welcome you all to this webinar on climate change and sea level rise impacts on Pacific Island countries. Let me commence by acknowledging the traditional owners of the lands on which we meet, wherever that may be, and pay our respects to their elders past, present and emerging. The Hub provides a forum designed to promote humanitarian engineering in international development and disaster response, and connects individuals and communities from government agencies, industry, academia and civil society, and encourages the practical learning and collaboration across the whole spectrum of the humanitarian sector. Now, the rules for this webinar are simple. I need to remind you, firstly, that the event is being recorded. And secondly, our schedule has time for questions at the end of the presentations. Please make use of the Q&A function to pose your questions and comments, and our panelists will address as many as possible. If there are some left over that are not addressed, then we will circulate the responses to those anyway. This webinar today addresses what has become a huge challenge for countries in the South Pacific, the impacts of sea level rise resulting from climate change. The impact on lives of those involved is serious and far-reaching, from loss of land, increasing disaster risks, threats to food and water availability, loss of coastal infrastructure, and more. We have gathered experts to discuss this vital topic, including from impacted countries who are living the challenge. You have their bios in the notice for the webinar, so in the interest of time, I'll not repeat that information, but simply invite them to present. And our first expert is Dr. Leanne Webb. Leanne is the Science Lead Pacific for CSIRO's Regional Climate Projections and Applications team. And Leanne's topic that she will be addressing is sea level rise in the Western Pacific, observations, projections, and specific country examples. So, Leanne, the floor is yours.
Thanks very much, Richard. Yes, thank you for the introduction. So I'll share my screen, which this one. Is that good? You can see that?
Yep, all good.
Okay, great, thank you. So as introduced, I'm talking about sea level rise in the Western Tropical Pacific. I've got some observations and then discuss a bit about projections and then some country examples, as Richard has just stated. Okay. So let's look at some sea level trends. I've got a map here that shows both altimetry, which is from satellite, and also tide gauge measurements. All right. So this plot shows the trend from 1993 through to 2025. The dark boundary layers are each country's exclusive economic zones. And then you can see the shaded map in the background that shows the altimetry. And then the dots within each of these EEZs shows the tide gauge recording. The red colour indicates the highest rate of sea level rise in millimetres per year across this time frame. You'll see in some of the countries, the tide gauge is measuring a different rate than what the satellite is measuring, and I'll explain that in the next slide. Where is one of the factors you need to consider in the Pacific is not all the land is vertically stable. Some is moving up or some is moving down. And you can see where the tide gauge and altimetry do align. For example, the Marshall Islands at the top It's because the land is stable. It hasn't moved up and down overall over that period of time, 1993 to 2025. If you look at Samoa, however, there's been a big decline in, or the vertical downward shift in Samoa, which has exacerbated the sea level rise. And in contrast, Vanuatu has been moving up, and that has made the sea level rise appear less by their tide gauge. So when you're looking at sea level rise in the Pacific, it's good to consider all sorts of things that will affect how much the sea will actually or may impact on the land. Looking into the future, we've got to consider some uncertainties. There's three sources of uncertainty. The first being the future greenhouse gas and aerosol pathways, which could range from low right through to high. There's also the regional climate responses, or the model responses to these pathways, some models being more sensitive to the shift in the change in composition of the atmosphere than others. And ongoing natural climate variability will occur into the future. So that is also considered in the future modelling of sea level projections. All right, so I'm introducing here these elements called shared socioeconomic pathways, or known as SSPs. And you can see the high SSP 585 follows this higher or faster increasing rate of CO2 increase. With the SSP 126, we call a low scenario, where there's a decline in greenhouse gas concentrations into the future. So remember these, because in all of the following or the follow-up, I'm going to be discussing SSPs. So the high is 585, the low is 126. Oh, 226 in this case. So this here, this shows the IPCC projections of global sea level rise out to the year 2100. And here you can see two pathways out into the future. The pink band shows the SSP 585 trajectory of sea level rise in centimetres, right? So you can see for 585, depending on the model, which shows that range of the pink coloration, it could be up to or more than a metre globally into the future, but the median showing around about 80 centimetres. That's the median of all the models. Where the lower trajectory of greenhouse gases, of course, causes lower sea level rise into the future. Now, what contributes to sea level rise is there's a lot of factors, including both Antarctic and Greenland ice sheet melting, glaciers melting, thermal expansion of the oceans, and also water stored on land coming out of the land and into the sea. And here you can see the contributions for the different timeframes, including the current timeframe, and what of these factors contributes most to the sea level rises. And what you'll see is the largest contribution is from thermal expansion of the ocean. So that means that seas are getting warmer, and that causes sea levels to rise. But there are other contributions. So you can see that overall, the main contribution, no matter which trajectory or which time frame, is the thermal expansion. But notice by 2050, the scenario doesn't matter too much. You can see even in the median of the scenario, sea level rises. There's not a big difference. It's the difference in scenario that matters a lot out into the by the end of the century, where of course the higher emissions has much greater impact. All right. The other point I'd like to make is that the rise in sea level is not like a not like bath water. It's not even everywhere. There's some parts of the globe, and this comes from the IPCC Interactive Atlas. You can go into this atlas. Anyone can go into this atlas and have a look. All right. Here I've selected a reasonably high SSP. So this is we'll consider the high SSP, 8.70 rather than 8.5. And this is by the end of the century, but you can have a look at all stages into the future if you wish to explore this sort of information. But notice that some parts of the globe tend to have much higher rate of or level of sea level rise by the end of the century than other parts. Okay, it's quite a dynamic science that does these estimations. You'll look, if you like to make an eyeball average, you could probably say that the Pacific regions sort of tends to be in that average of the whole global sea level rise outlook. But there is another tool, a really interesting tool that has been developed by NASA. And this actually doesn't measure sea level rise, it measures sea level change because it factors in the vertical land movement into their tool. So it's quite a helpful tool. And what you can do if you're in the Pacific or anywhere, again, this is global, anywhere in the globe, you can actually click on any of these dots. All right, I've just, for example, picked Samoa here. And you can get the full projection of sea level in this kind of time frame. You can pick, here I've just picked the low and the high emission scenarios. All right, this data is also available tabulated, so any engineers can grab this data. It's all tabulated. You can, and here I've dialed just to have it, by which January 2050. This is the different median results. So it's quite an interesting tool to use, especially for engineers, I think. And it has this other interesting aspect where it shows the timing of sea level rise milestones. Again, because we don't know about the emission scenarios into the future, we have to consider all of those. But you can see, for example, in Apia, I've chosen a meter, but you can, again, this is a toggle button. This is a screenshot toggle button that you can pick 0.5 of a meter or 2 meters, whatever you might be interested in as an engineer. How by when will this be exceeded? All right, so the exceedance threshold of 1 meter. And you'll see under the high warming or high emission scenarios, this is exceeded more or earlier than the low emission scenarios. It's just another way of thinking about the problem. All right. The earliest that this could be exceeded is called this 585 low confidence threshold or emission scenario. And while this is, I'll explain what this is. This low confidence is what people might be talking about when they talk about the climate change tipping points. And for example, things happen with Antarctic ice sheets faster than, and that is factored into these scenarios where it's actually it's low confidence because the science is still being evolving in looking at ice sheet and how they will evolve into the future. But it's sometimes a factor that engineers might have to consider when they're planning and designing, especially some very long-lived assets. So it's something that you can consider, but something you have to consider with a bit of caution. Okay. So let's talk about extreme sea levels. So that was just sea levels, all right? But what causes extreme levels is there's also other contributions. I notice engineers would definitely take this into account. For example, tides, the interannual sea level variability, and ENSO is a big factor in the Pacific in this because that's exactly where that warm water is shifting around. So where the warm water shifts in these ENSO phases is, of course, got higher sea levels. All right, so that's a factor. There's also storm surge and then the waves that occur, for example, with tropical cyclones, right? So these all, and also coastlines and the run up and all of the shape of these coasts are also important to consider. Noting that, and as people will probably be aware, not all extreme sea levels occur because, for example, a tropical cyclone might occur just by chance and luckily when it's not high tide. So while there's a TC, maybe that doesn't cause an extreme sea level event. Just a couple of examples to finish. So I've got some, we recently did some work in Tuvalu, which is very exposed to sea level rise given its low-lying nature. So here in this Tuvalu work, there's been some inundation modelling undertaken by the TCAP project. There's a, you can see on this, there's a web link for that. You can get some information. That was the LiDAR modelling, but we developed that further and had a look at different things like population exposure, the cost of different exposures at different times, and also picked out a few buildings that are important buildings in Tuvalu. And here's an example of the Parliament House. You see in that list there's all sorts of buildings that we've done this kind of modelling for. But for example, and I think people might be familiar with return periods. What return periods means is how frequently an event will occur. So if it's a 5-year return period, that means it's reasonably frequent. These kind of events occur every 5 years. Compared to, for example, a 100-year return period, they're rarer. It's in the statistics. They only occur about once every 100 years statistically. And you can see here, for example, this Parliament House, and the current climate under 5-year return period doesn't impact these storms that occur once every 5 years will not impact Parliament House. But by the end of the century, even the 5-year return periods will impact Parliament House. So that's we would consider that well exposed at the end of the century. And this is under the middle SSP 245 scenario. So this sort of work's being done all the time, or in many of the Pacific Island countries. This is also for Tuvalu showing population exposure, different islands in the archipelago here. And you can see all the different islands, this is 245, by the end of the century. So this, pretty much this column, okay, 1 in 100-year return interval. So by the end of the century, under middle climate emissions, there's some islands in Tuvalu that show that they're more exposed than others, where I can't just Neuto, I don't know how to pronounce that, is less exposed, for example, than other islands in that chain of islands making up Tuvalu. Another really interesting project that was undertaken recently in Vanuatu is some LiDAR mapping that shows exposure to roads in Vanuatu. And this is, again, you have to, in this space, you understand frequency of storms is how we describe how dangerous they are. So this is a 1 in 50-year storm, and how and where it will inundate the coast under current climate versus high emissions by the end of the century. So this kind of mapping is now being developed for Vanuatu, and they're using this mapping to start planning their roads for future. And all of these have been reported in some really accessible documents available on the Vanuatu Climate Futures portal. Thank you very much. Sorry, stop sharing.
Okay, thank you so much, Leanne. That was very informative. Quite a lot of information and references where engineers can go. We do understand return intervals as engineers, and I think, understand what you're indicating there. So thank you so much for that, for your presentation. And we turn to our second speaker, who is Eldon Teepa. Eldon is based in Kiribati as Director of Architectural and Building Engineering Department under the Ministry of Infrastructure and Sustainable Energy in Kiribati, as well as team leader for the DFAT-funded Kiribati Australia Infrastructure Program. So Eldon is very, very well qualified to address us on this subject. And his address is Kiribati from Code to Coast. Quite an interesting title. So over to you, Eldon.
Hi, Richard. Oh, Dix. Just checking the microphones going well. You can hear me clear? Apologies, I know it just came in. So if you can hear me, give me a
Yes.
thumbs up and I'll
It's
share my
all great.
screen. Perfect. Thank you, team. Appreciate it. Okay, I'll share my screen, and then we can go from there. All righty. Awesome. Okay, so basically, thanks for the introduction. As the director of, well, I'll call it ABET to keep it short, and also the team leader for the Takai program, I've been fortunate enough to work in Kiribati. I'm a fierce Wallaby supporter, although we do struggle from time to time here to work, under DFAT, but also support the ministry in this very important aspect of being the director. And it's important because we've gone through some massive policy changes. And it was great to hear, Leanne, the science that's behind climate change. And I don't dispute, I see it firsthand here, where the highest point on South Tarawa, where I am, is only 3 meters high. So, it's there's no mountains here. So it's very important for us to understand what's happening and tracking the science. But what's also important is being able to have policies that we can implement. So today, the whole focus for my discussion today will be looking at identifying the middle step. So not the code, not the coast, but the actual two. How do we implement that? So recently, Kiribati has undergone policy change, which I've just advised, and it's the new Kiribati Building Code, which references a lot of the Australian and New Zealand standards. So it's basically, as it is with every other country, a legal framework that allows us to operate and build buildings that are fit for purpose. And in this case, they're fit for purpose to ensure that we have climate resilient buildings. So that impacted a lot of the designs. There's things in the design requirements now where it's supposed to be the minimum floor finish or the minimum floor height should be 1 meter from the ground. Now, the practicality is it's not happening on the ground. So whilst we're about to start, we've got to try and shape a whole country's perspective on how the code should be met. Why it's a meter? We're trying to change the mindset of the local counterparts, the contractors, the people, is one of our key challenges. Trying to implement these solutions. Having that evidence-based design basis and material suitability, these things are key for us because in Kiribati, there's a lot of materials that are imported. Our economy is heavily tied to Australia, China, New Zealand's material market. And we'll touch base on something that's critical for us as well, because if we're looking to build quality infrastructure, we got to have the price to match. However, the economy doesn't quite allow it. So there's a heavy dependence on international development partners to actually support that. Um, okay, so proportionate pathways. Basically, we're looking to facilitate a staged process for implementation for our building code, because if we were to make it happen now, most of the projects right now would be non-compliant. So we do have a plan in place to stage them. Like I said, when you're working in international development, in international development space, the market itself, the governments, the local construction market, the local engineers, there's a heavy dependence on experts coming in to deliver the work. So the quality of the work has to happen. And if it's not there, we don't get the quality outcomes. We don't have, properly built seawalls, properly built bridges, roads. We're looking at baseline data such as flood levels. We're looking at structural designs as well. There's a heavy reliance on international development partners to supply that. Currently in our ministry, there's a limited number of certified practicing engineers or, fully qualified experts who can support. So that dependency once again hinges on what development partners can provide, and that ultimately also affects sustainability. Like comes back to the reliance on international development partners. When we're looking at material suitability in Kiribati, it's a massive thing for us. One of the key challenges we have on the ground to build like sustainable infrastructure is aggregate. I know there are studies that have been done around aggregate. We have one company here that provides it. However, there's a high salt content in there. And so when you're going to mix it with concrete and applying it on the site, it doesn't last. We have one classic example in one of the towns, Bairiki. The building was built, however, it wasn't monitored properly. It was a three-story building that ANZ were in. Now, because of the salt, the corrosion on the steel, it's no longer viable. People, they've all moved out. And that comes back to just poor systems, poor oversight, lack of quality materials or availability of quality materials. And if there are materials, there's a lack of policies and processes on how they should be processed to ensure that they are fit for purpose on the ground. So there's some of the implementation gaps that we face from the code, down to policies, down to actual resourcing to staff. And so it's critical for us to monitor that on the ground. The cost and feasibility, once again, there's a heavy reliance on us to actually go find funding. So we'll have these designs that we really need. For example, solid causeways. However, once again, it comes back to aggregate. We need to import most of the materials, probably 90%. If you think about where our material costs, where they come from, it comes from Australia, New Zealand, it's already at a high price. Then we have to pay for shipping, pay for, import costs as well, clearance costs. So it all starts to add up. This is exacerbated when we have to go to an outer island. So the first port has to come to a South Tarawa. If we've got a project in, say, Butaritari or another outer island, there are further costs that are involved where we've got to ship it over there. And so you can see that building quality starts to build up the price. And so for a government, it's not feasible to deliver. Hence, again, the heavy reliance on international development partners and trying to make it work. When you're forced to build under these conditions, it is a challenge and a half. And every day we battle these things to try and figure out what's best, what do we drop off, how do we slowly change the hearts and the minds of the people to understand that we are trying to build something quality whilst making it affordable. One of the key things that I forgot to mention earlier was our Building Act specifically states that the Act and the Code only applies to South Tarawa and Christmas Island, for the sheer fact that that's the massive economic hub. And that's where a lot of the companies and people, that's where the money's at, so they can afford it. All the outer islands don't rely on that. However, there are some plans in place to implement building manuals to support the outer islands that don't fall under the Act. So product testing and evidence. Another issue we have is the only material testing lab in the country. Like most other Pacific Island countries, they're under-resourced. Our one's pretty much not functioning. And so a lot of our tests in terms of our concrete or compression tests and that, we have to send them out to Fiji to get it tested, or companies like Fletcher or Reeves bring their own equipment and they do their own testing as well. If they're here and they're the assets, we can use it. If not, then cost again is increased. There's a lot of issues around contractors as well in terms of the quality of the contractors. It's like a two-speed economy here where you have international development partners that come in and deliver their big projects, but how do you maintain it? And then how do you get local contractors with the capacity, the skills, the fiduciary acumen to manage that business, to make sure that their business is going so they can service these infrastructure projects and have a solid asset management plan to back. So trying to support our local contractors for sustainability is critical for us. And we're doing a lot of capacity development, not only in the ministry, but in the local market to ensure that they can meet the demands of the designs. Operations, maintenance, renewal. A big thing in last year's Pacific Infrastructure Conference was working in asset management planning. It is a big thing here because there's a heavy reliance, once again, on development partners. Every time there's a new project, the question I get asked is, who can you go ask money from? So we've got to do proposals. Then the next question we get back is, all right, do you guys have a maintenance plan for the bridge? Do you have a maintenance plan for the causeway? Do you have sinking funds allocated? Is there a policy or a financial policy that allows for this to happen? And the answer is no, we're working on it. So trying to catch up while delivering, quality infrastructure is one of our challenges there. A couple more slides, won't be too much longer. So generic standards is not enough. The resilience is in the details. One of the key things we have is if we've got the science telling us that we need to build higher or change the way we do things, the code comes into place, but it's not the code that actually builds, it's people. And one of the key things is engineering on the coast, like looking at these elements here. Yeah, they're all from the code, but having the team that have the expertise, experience, having contractors that have the experience and the financial capacity to meet those demands is difficult to find here in Kiribati, and I dare say in a lot of other small island development states. Our processes internally to ensure that they're fit for purpose also have an impact. We have a team on the ground who are learning, they're great, but experience once again is limited, and having the capacity to go out and inspect, to have them understand what they're looking at is a challenge. So there's some good news, don't worry, I'll come back with that one. So from the last, from my last slide I'll share is just from publication to protection. Looking to clarify the roles internally. So how are we going to shape this? Clarifying what each department has to do, what each ministry has to do. We're currently finding our feet. There are laws in place, there are role delineation policies and whatnot, but it's still unclear. And that sort of confusion internally affects how contractors engage with our ministry, how they engage with other ministries. As it is with every other, like a lot of Pacific Island countries I've worked in, it's not a straightforward build. You have to go through multiple ministries, through different sub-departments to try and get the job done. And it can be a challenge when it's not clear. We're looking at simplifying it by using the building manuals. PRIF have been fortunate enough, and World Bank's fortunate enough to be funding that next phase of our implementation plan. So we'll be doing building manuals for the outer islands, but trying to incorporate and teaching families that, hey, this here is to ensure that your building, your homes will last longer. You know, at the end of the day, it's their choice. How do we convince them that that's better for them? When, you know, the cost may be, say, 100K versus, oh, they can do it with local cheap materials for like 20K. And so these are some of the considerations you have to make when we're talking about policy. When you're trying to implement the code, make that cultural currency is vital, because we can talk about policy, we can talk about the science behind things till we're blue in the face. But in the Pacific, there's a very, very important factor, and that is cultural currency, because if you do not know how to navigate that, it'll be difficult for you to affect positive change. And the key reason why I share this is development partners have been in the Pacific for the last 15, 20 odd years, maybe more. And if you're looking at a return on the investment, this is one thing that is significantly overlooked. And the same issues happen. Why do we not have these things moving forward quicker? Why can we not have effective change? You know, why can't we implement our code? And in saying that, you know, the whole point of this is to the objective of our work is to ensure that people have safe places to live. People have access to affordable materials so they can build. People have access to affordable or solid infrastructure that's maintained long term. And at the end of the day, in the Pacific, we can have all that, but to affect
We're
to
starting
make
to
sure you
lose you there,
expatiate its
Eldon.
efficiency and effectiveness, understand that cultural currency and navigating that is important experience here in the Pacific. So that's all I want to start implementation, and happy to take some reason. I apologize here.
Thank you very much, Eldon. That was very interesting. To learn how a government can develop policies to address the problem and apply those through the code that it develops. And you introduce the concept of cultural currency and the fact that contractors must meet quality standards if you're going to have buildings that will last. And that I guess applies anywhere. So thank you again. Now, our third speaker is Scott Keane. And Scott is the uh,
It might
he
it
has
might be it might be Anthony. I'm not sure.
oh, we changed around. Anthony, are you ready to present?
Yep.
Okay. All right. Sorry. Relax a moment, Scott. It is Anthony V. Uh, and for the benefit of the the wider audience, I'll advise you that Anthony is actually in Utah at the moment because his wife gave birth two or 3 days ago to their second daughter. So he's over there celebrating a wonderful event in their family. Anthony is a project engineer with the contractors McConnell Dowell, very well known, long-standing major contractors, New Zealand-based, but operating throughout the Pacific and in Australia. And he has direct involvement with in Tonga. He is from Tonga, and he has direct involvement there in two major projects, the Queen Saloti Wharf and the Whanga Uta Lagoon Bridge. Now, the subject that Anthony has is a contractor's perspective on working in the South Pacific. So over to you, Anthony.
Thank you, Dick. John. Good afternoon, everyone. My name is Anthony Vea, project engineer from McConnell Dowell. Firstly, just want to thank Dick and John and the Warren Center for having me on as a panelist on this webinar. So I've worked for McConnell Dowell for 8 years now, starting with them in New Zealand right out of university. For the last 4 years, I've worked in the South Pacific. So when I started in the South Pacific, can we move to the next slide? Sorry. I was a site engineer at the Mala Base Wharf upgrade in Vanuatu, which was a wharf funded by the Australian Defence Force, upgrading wharves all across the South Pacific for the new Guardian-class vessels that they were donating to those countries. After my little stint in Vanuatu, I moved on to the Queen Saloti Wharf upgrade as a site engineer, going to senior site engineer. This one was a personal one for me, having been from Tonga originally and then moving to study in New Zealand and then being able to make my way back to build this modernized, resilient structure that's basically Tonga's lifeline, responsible for over 90% of Tonga's imports and exports, was true blessing. And then just recently, after completing the Queen Saloti Wharf upgrade, I've moved on to the Whanga Uta Lagoon Crossing project, which is basically a 600-meter long bridge running between the two yellow cranes you see at the bottom of your screen across the lagoon, and an additional 2.5 kilometers of road, which is a significant piece of infrastructure for everyone in Tonga. We build ports, wharves, but then not everyone gets to see it. So this is something that's really significant for the whole country. It's also a key evacuation route out of the main town area over to the bush areas, which are higher in elevation. It's quite funny on this. I believe the reason this was fast-tracked was because in the 2022 tsunami evacuation, the prime minister at the time was stuck in traffic trying to leave town. Just why I believe we are building this right now. Wanted just to go through quick, everyone may be aware of it, but how these major infrastructure projects are funded and go into the construction phase. So firstly, financing is approved by the bank and the host country. They go through a project preparation and feasibility study, then into detailed design and procurement documents, which then moves on to the tendering process. This is when the contractors finally get involved, and they may go full investment or partially, just to see what their risk is. And then there's an evaluation process, and then the contract is awarded to the contractor. And then finally, construction commences, contractor mobilizes the site. I just bring this up because, You just see later on in the stage is when the contractors come to site and when delivery is required. So there are issues that we have to deal with very quickly. Design solution to deal with sea level rise. I think everyone knows we just make taller structures. Sea level rises make taller structures. The points I want to discuss today from the contractor's point of view is the survey control. So sea level rise results in an increase in mean sea level. How is this translated to the country's survey control? Tie-in, confirm on site. Probably a contractor's least favorite thing to see on the drawing is a statement that says confirm on site, because it means that there are some design elements that haven't been finalized yet. So we need to confirm it on site when we're there working together with the designer. So when you design all new structures to be higher in an elevation to account for the sea level rise, you have to tie it into existing structures because there are extents to, financially to how much you can build in a project. And then the height versus cost scenario. So the cost of building structures taller increases due to the methodology required to construct. So if you have a design life of a wharf that's say 25 years, you have to deal with an incremental rise in sea level. Whereas if you deal with a design that's 100 years design life, then you have to deal with a larger sea level rise, which means you'll likely be designing a taller structure. So survey control. This TON1 benchmark is a control point just south of the Queen Charlotte Wharf, which we used on the project as the main benchmark for our survey works. This TON1 benchmark isn't just a local benchmark, it's actually part of the wider Pacific Sea Level Monitoring Network and has immense value for sea level climate change worldwide. Our elevation was based on MSL, so mean sea level. So a 0-meter MSL meant that that was mean sea level at that time. We moved on to the Whangauta Lagoon crossing, and we received this tide table as part of the design documents, which reference a different datum, tide gauge 0. It had a different mean sea level value, 1.042 meters. So after dealing with all of this at Queen Charlotte and then coming to deal with this at Whangauta Lagoon Bridge, we decided it would be best to translate this datum here to the TON1, which is a significant benchmark that's used all over the South Pacific. What we learned from this translation is that there was a 92 mil difference in mean sea level from the Whangauta Lagoon crossing tide levels and the Queen Charlotte tide levels. So we made an adjustment and went with a more conservative approach, which resulted in a 92 mil increase in all elevations, including the bridge and roads, which could add significant costs to a project. So with all the value engineering proposals, we worked together with designers and the government of Tonga to come up with a solution that works. Next, as I mentioned, the tie-in and confirm on-site scenario. So this is the Queen Charlotte Wharf, which we had just worked on. Down on the southern side of the wharf is this red line, which is the extent of the Queen Charlotte Wharf project, tying into the existing structures. Up by the gatehouse entrance here, they accounted for the steep slope and change in elevation by running a table drain across the gatehouse here. Further down to the southwest corner here, where we had just tied into the existing level, there's a steep change in elevation here. So there's major surface water runoff, which goes into the existing pavement. Sometimes the existing infrastructure cannot handle this type of change. So this area floods if there is a major rain event, and then eventually disappears. But I would say in the next run of funding, when Tonga is able to extend their wharf projects, they can deal with these issues. Finally, the cost versus height scenario. So Imala-based wharf upgrade was a 25-year design life, because in 25 years, they'll have newer boats and they'll need to most likely build a bigger wharf. The top of headstock was somewhat around 1.5 meters above water level, which was very easy for construction and gaining access to the area. We just pulled around these floating pontoons, ran them across the piles, and we can sit there, install these headstocks, and work in this area. In another scenario where we're going to the Whangauta Lagoon crossing, which its height accounts for sea level rise and a bunch of other things, but just to touch on the sea level rise, the top of headstock is 4 meters above water level, which then requires a significant temporary works procedure and temporary works fabrication to be able to construct these headstocks. So you can see that it's not just the materials that you're dealing with, it's the construction methodology and the cost of the temporary works that will skyrocket the price to build these items. Those are the main 3 points I wanted to talk about on the contractor's perspective. I also wanted to touch on how we, Mokono DAO, approached the project with Queen Charlotte Wharf. We came into Tonga in 2022. Luckily for me, I was coming home, so I was able to get in touch with everyone and set up contacts, but we were able to develop a workforce. So we direct hired all our employees to work directly for Mokono DAO. We identified local partners to support deliveries. So that's quarries. We had 3 or 4 quarries work for us and deliver aggregates for the batch plant and all materials required for construction. We worked with the local community, building. When there was flooding, we put out all our additional pallets down to create a walkway for all the children to get to their class from the parking lot. And then we live, work, and play in Nuku'alofa. So we use the expats that come to Tonga and work there. We participate by going to the local rugby games. We use the local facilities for leisure, like playing basketball, that fun stuff. Training of the local workforce. So at the end of 2025, we had over 3,000 hours of training hours. And for the high-risk construction activities, we had certified trainers come from New Zealand to carry out this training. And what this does is it gave certifications for all our workers so that once they move on from Mokono DAO and go to work in New Zealand, Australia, they know that these certifications are still valid in those countries. We also did a lot of social impact and issues training. This was quite good to do as this was done by the Women and Children Crisis Center in Tonga. So this is a group, Tongan organization training a Tongan workforce. The bottom left here, we've had the Tongan Red Cross come and carry out the first aid training. And on the bottom right corner, the Tonga Fire Department came and did fire extinguisher training on site. And that's all. Thank you very much for your time. Appreciate it.
Thank you, Anthony. That was excellent, and you've. It's interesting that you raised the point that perhaps I hadn't considered before, that the rising sea level does impact on the base level that's adopted, and will continue, I guess. So we'll move on to our 4th speaker, who is Scott Keane. This time I will introduce Scott. He has a long experience in port and marine sector in the Pacific and Australia. He is market leader ports and maritime for the major international consultant Stantec. And I have to acknowledge that I worked together with Scott for many years in Cardno. Scott is also the International Vice President and Maritime Commission member of the World Association for Waterborne Transport Infrastructure, PANC is the acronym. So he has a strong connection internationally there. Scott's subject is engineering infrastructure to account for sea level rise. So over to you, Scott.
Thanks, Dick, and thanks everybody for the invitation. I assume everyone can hear me. I have a lot of slides, but I'll be moving through them fairly quickly. Unfortunately, being the last speaker, lots of people have covered things that I was going to speak about, so I can flick through pretty quickly. I will talk very briefly about why SLR matters, and that's been discussed by several other speakers already. Some other considerations, and then particularly around future proofing. So, why does it matter? So, we've already heard about being infrastructure in the Pacific being a lifeline, and that's quite clear to everyone. We know that sea levels are impacting community areas, crops, water supplies, and everything. And I have seen that firsthand, as have a number of other speakers that have already spoken today. There's also the fact that erosion and wave impacts are affecting structures beyond what the design intents were, and changing sediment transport and recovery mechanisms on islands that are having significant impacts on livelihoods, access to transportation, and other things. So typically in the Pacific, we see a lot of cases like these where communities, small island communities, are reliant on small vessels transporting either to schools and the like, or to larger vessels for their goods supplies and frequent provisioning and the like, or getting product to market. Sorry, I'll just go back a slide there. But that comes with challenges when you're dealing with being significantly offshore and the like from main island infrastructure and trying to get that even across coastlines. Last year, the Tuvalu Minister for Climate Change made a very strong point for COP26 by standing in the water to make a presentation. But Tuvalu, we all know, is one of the most impacted locations at the moment, and I think Leanne showed that quite clearly with the challenges that they face. So a lot of photos that I show here are actually based on Tuvalu going forward. I'm not going to try and challenge my bandwidth at the moment, or maybe it will work. Leanne showed previously about some of the issues that we deal with when we're considering infrastructure and the like, with wave setups and run-ups and the like, and storm surge. This video, which I assume people will be able to see when this is shared later, really shows that this house near shore is impacted significantly by that run-up during a storm event. Similarly, have a brief presentation here. This is based on a sea level rise scenario of an infrastructure project in Australia. You can see on the slide here that there is a seawall shown, and it shows that because of the sea level rise and the run-up and the increasing severity of events under climate change scenarios, the frequency of discharge over the top of that breakwater or seawall. These are the sorts of things that we need to consider during design. Now it doesn't want to move on for me. I mentioned previously about the challenges of shoreline change and sediment transport. So this shows quite clearly and quite nicely over a long period of time the substantial changes that happen to the vegetation line on a small atoll in Tuvalu. But nonetheless, if you've got infrastructure on that island, you've got to actually think about how that impacts over time and how you try and future-proof that. But also how you protect the communities that are actually living in those locations. Similarly here, so this was a recent project in Ebi in Marshall Islands. So you can see that to protect the community from sea level rise and shoreline issues, particularly with storm surge, they did a massive project in terms of seawall, and that required importation of material, among other things, as several speakers have talked about the challenges of local supply of materials. This slide, in actual fact, was the material being bought in for that particular project. So this material, regionally, it's very difficult to obtain. I think Eldon and Anthony both spoke to that issue, but this material actually came from Dubai in large cargo vessel and then used smaller vessels to relocate that to shore. So some of the issues that have been talked about by people already, funding, obviously. We have real problems throughout the Pacific. So some of these locations, very small island communities, small number of people that benefit from this, but nonetheless, it is transformative and it's all about sustaining life in a lot of cases. People have talked already about local capacity to build or maintain these assets and the local materials. So a recent project that we worked on was Nauru, for example. Nauru has abundant supply of limestone rock, and the country wanted to make use of that material. Unfortunately, when it came time to supply in the quantities that were required for the construction, they couldn't do so, and at substantial increase in cost, they had to pivot and change their construction methodology for the seawalls. This project is another project in Tuvalu, where it's a fantastic facility. It was already there, but fantastic facility for the locals to be able to gain access to the water for loading small vessels in and out and for major cargo. Unfortunately, it had silted up. So as you can see, the channel that's now been cleared as a part of this project didn't exist. So people actually had to trudge and take drums and everything else from where the shoreline had actually accreted to. And as I mentioned before, the challenges of importation of material, and it's sometimes at significant distances. So if I pivot to the main topic that I really wanted to talk about was challenges in design. So upgrade versus future proofing. So Anthony just spoke about, obviously, if we design for 25 years versus 100 years, for argument's sake. But it's not always that simple. Oftentimes we come in, it's not feasible to change the infrastructure, so we actually have to reinforce it or raise the levels of it or whatever else. But again, this photo on this slide just shows that's GRP reinforcing, so fantastic because it doesn't corrode. It's not always practical in the Pacific because of seismicity. We've done projects in the past that use stainless steel reinforcing, for example, but when you're talking about 4 or 5 times the cost of normal reinforcing, it adds a substantial cost to your project. So some of the challenges that we have in design versus future proofing. So climate change is fantastic from a port engineering perspective because you don't need to do as much dredging, but it's not so good in many other aspects. So as I mentioned before, possibly greater sediment transport, existing wharf uplift or overtopping. So when you've got sea level rise and you've got wave action underneath the structure, that can cause massive issues. And perhaps the structure hasn't been designed for uplift of the structure or the piles, for example. Maintainability, the berthing loads, and in the Pacific, seismicity. So you go for heavier structures or lift deck height and add extra load to it. That may make it more prone to seismic failure in a seismic event. We have things like nav aids that are relied upon by the communities to find their way home between islands. And that might mean that the light is now closer to the sea level or impacted by wave action, so people can't actually see it. Coastal defense, so I mentioned that before, it may not be practical to build higher because that on a normal revetment builds out further. So you might actually have levels that drop off a reef or something else. So you need to then think about seawalls and engineering them to withstand massive wave loads. Erosion and sediment budgets. So some of these locations are being impacted over time by erosion that then impacts on the local communities and the very land that they actually exist on. So if that is the case, we need to look at reinforcing those areas, adding more sand into those environments or rock to protect it so that there is material in case it erodes in future. And access now versus in 50 years' time. So some of these facilities, for example, are relied upon in very small islands, by way of example, by the infirmed, the elderly, kids going to schools. So it's not always practical to build for the 100-year design solution now. You may need to think about the now and how you adapt it in future, which then brings into account those other things that I've just mentioned. So a case in point, in terms of loads, I don't want to bore people with too much engineering, but if you look at this slide, on the left is free sea level rise. On the right is allowing, say, a 0.6 metre sea level rise. You can see that the piles in this particular case would have to be designed quite differently. So the point of inflection in your moment is at a different height. But the big difference is in this particular case, which was only a very light load without any seismicity or anything else, it's about a 5% difference. And your pile design would have to account for that. We've had cases anywhere up to, and particularly when you add seismicity and other things to it, you could be dealing with 25% change in capacity, and that's massive in terms of whether you allow for it now or into the future. Similarly, I talked about revetment. So you may be able to build up and out further. So if you had to increase your height, build up higher, that pushes your toe of your seawall out further. That might be possible in some cases, but it may not. It may be across sensitive areas, fishing grounds, whatever else, or off the edge of a reef, in which case you've got to design a seawall. Or it might be a combination of factors. So a combination of revetments, and seawalls, wave dissipation devices, a range of different scenarios that you might have to consider. The uplift issue, and this is a massive structure, so this is an Australian project, but just by way of explanation, during a recent storm event, and because of some sea level rise since the design, the storm actually popped all the decking off this particular structure that was being built at the time. And this has been seen across particularly cyclone-prone areas around Australia. But nonetheless, it's something that needs to be considered now. So if we're thinking about sea level rise, as I said before, it could be the piles, it could be the deck. You need to think about how you hold those down, whether the piles have been designed for it, or it could be for overtopping, so significant wave action on top of a deck, and whether that actually does other damage and design actions that you need to consider. This was a very simple design, for example, that thought about your ultimate deck heights, so design vessels at low water and at high water in a current scenario, but then also for sea level rise scenario. So in the sea level rise scenario, you can see that you can actually access still, and it's still functional, but unfortunately it may not be all that practical for people in the meantime to actually, particularly elderly, infirmed and the like, to actually get on and off vessels necessarily. It's okay if it's cargo vessels. There's another project, similar sort of arrangement, but again, it's a major structure with a stepped profile, so that at different stages of tide, vessels could come alongside, tie up, and people get on and off, or with cargo on and off. That's a little bit simpler, particularly for those school kids or the elderly, infirmed, pregnant women, all those sorts of things that we have to consider throughout the Pacific, right? So this was a project in Tokelau, for example, very similar sort of arrangement. So providing some protection to the channel, so you stop some of that coastal accretion and the sand accumulating so it's maintainable. Different areas to protect from wave action coming down the channel, and then different aspects of the wharf for either cargo vessels or smaller local vessels and things like that. So a lot of thinking. It looks like a really simple structure, but a lot of thinking has to go into it to not only come up with a practical outcome, but also cost effective and long-term sustainability. Dick mentioned PIANC. So for those that don't know, PIANC is the World Association for Waterborne Transport Infrastructure. So what does that mean? It means that we have a number of commissions, we call them, but people that come up with design standards. So our Environment Commission looks at environmental aspects, but also has a task group on climate change. The Maritime Commission that I am involved in directly comes up with maritime guidelines and standards for construction. We have an inland waterways one, which doesn't mean much to anybody in the Pacific or Australia. And we also have a cooperation commission that looks at developing countries and how we we benefit and share knowledge with developing countries. So we mentioned just before that, or in the information that went out to everybody, that there is this has now been released, this guidance document, so guidance for ports in small island countries. It's very much an advisory document. It doesn't go into a lot of technical information. The technical information sits within a number of other working group reports and standards from PIANC. But what this document does do is goes into SDG goals around climate change. It talks about climate change impacts and adaptation. And then the concept of design and actually how you build in all of those aspects. So it's a really important document. There's Pacific examples. There's examples from other ocean developing country island states. But the Pacific was the largest contributor to this particular document. So thank you, and happy to take questions. Thanks, Dick.
Well, thank you very much, Scott. That was a very comprehensive introduction into engineering for climate change. Now we have a few minutes for questions. I should have reminded you all before to pose your questions on the Q&A. And you may still do that. We have one there at the moment from here, Joshi, for Leanne, who thanks Leanne for the presentation. The question is about return periods due to climate change. There are uncertainties about return period forecasts. I just wanted to know, in terms of modelling, how we are allocating percentage for such uncertainties and potential impacts. And Leanne, you might address that. Do I understand that the IPCC had a rethink of their the SSP 585? Is that correct?
Yeah, that's true, Richard. So the way we manage the uncertainties is by actually calculating them. Well, and engineers you guys in working on the ground might have different way of coping with this uncertainty, but for our modelling, we just usually present it under the different scenarios, because it's difficult. You can't really take an average of the scenarios, because that's just not a logical way of thinking about it. So we will present it under, if there's a high emissions pathway that the world follows, we look at this return period scenario kind of thing. All right. I'll get to your question in a minute, Richard, about 585. But one way that we've thought of for looking at these kind of questions about uncertainty is you look at the tolerance to risk, because certain parts of infrastructure you don't want to take much of a risk for. For example, the road that goes to a hospital, but for example, if there's a football ground, or there's certain parts of infrastructure that you have to consider that you don't tolerate too much risk, and so you probably look at the worst scenario and work with that one, right? Now, with regard to 585, and thankfully, it's looking less and less likely, because, well, it might not appear in the media that things are happening. They now call 585 implausible. We're tending to head for, best case would be we're likely to head for something like the 245 scenario, which is a sort of middle range. It feels currently at the moment where we might have skipped above the 1.5 level of global warming by the end of the century, but that hasn't been declared yet. It's just like the modelling is showing. We've already exceeded 1.5 above pre-industrial for 2 separate years, but not as a climatology. Okay, so yeah, so the way we work with it is sometimes you have to look at what you're managing to see how much you'd like to sort of avoid the risk. I hope that helps.
Yes, thank you. Yes, thanks very much, Leanne. Well, we now have other questions in the Q&A. From Lalitha Sahana, insurers are already applying risk-based repricing to high-exposure coastal property. I guess that might be coastal property in Australia, and I'm not sure. In some cases, the point of full market withdrawal. Is that repricing running ahead of or behind the actual physical risk trajectory? And depending on which way the gap moves, does it exhibit as a widening protection gap borne by the property owner, or does it eventually socialise as fiscal exposure onto councils and thus the general public and the state? I don't know where anyone, where any of you would like to address that. Maybe that's for Leanne also. So
I wouldn't.
Question is the risk to coastal property by as the result of sea level rises and climate change impacts.
So that's a bit out of my wheelhouse. I have to say it's more into policy decisions. Maybe have any of the engineers seen any of this kind of costing? Who pays kind of for these outcomes? It's an interesting question. I don't have an answer.
No. Well, it normally gets down to a lot of local disputation about whether people who have properties on coastal areas which are being affected by stronger storm surges and the like. You know, we have them on the northern beaches in Sydney, and they're very expensive houses that are put at risk, and there's a dispute about who should pay. Perhaps we'll take that one on notice. That question. There's a question: is there any slide shared? I guess the response to that is it not, John? That the slides will be shared. Is that correct?
It's entirely up to our presenters.
Okay.
Yes.
Okay. We'll let you know those who are registered. Richard Fackner, good day, Richard, has a question. He thanks you for the presentation. Does any of the climate change modelling include changes to water temperature and what that may mean for food, fishing? And secondly, he says, on a recent visit to the Pacific, I heard many comments re poor quality of imported materials. What steps are being taken? And that was something that both Eldon and Anthony referred to, was the need for quality because of the severe conditions that structures and therefore the materials are built out of are subjected to in Pacific Island countries. Is there, and Richard asked, are any steps being taken to ensure basic items such as cement and aggregate and steel must meet recognised standards? Perhaps Eldon, that might be one for you, and maybe Anthony can comment as well.
Scott's got his hand up.
So I saw Scott's hand go up quick, so I was like, maybe Scott, if you want to respond, then I'll just support you on that one. But I do have some to share.
Look, I can speak from an engineering perspective. We are involved, obviously, in preparing specs for these sorts of things all the time. And as part of construction, and as Anthony would be familiar, we're checking on those quality issues. So oftentimes there's very specific requirements around the types of cements. Certainly around the testing that's done on aggregates to make sure that they're not reactive in certain environments, to make sure that we do achieve the design lives that we're designing for. Hopefully that helps.
Thanks. Yeah, thanks, Scott.
I can throw my 2 cents there if you want.
Yeah, Eldon.
Especially around the materials. In Kiribati, aggregates are a big thing, but most important to get quality materials into Kiribati. It all has to be imported. Now, Scott spoke about the designs, and it's very specific, and he's absolutely correct. Achieve sustainable buildings and infrastructure if the designs are followed, but the materials that are specified in those designs and the construction methodologies within them, if you need plant and equipment, they all have to be imported, and that's the only way you can get around it. Currently, the local construction market and suppliers, we're capacity strengthening the local market as well to ensure that they bring in quality materials. And so they're some of the areas that we're supporting the local market and the country in providing quality materials to meet.
Yeah, just an example in Tonga, when I arrived in Tonga, I went to visit a few batch plants that were working, but they were loading everything manually. And after just a bunch of case studies and business cases, we decided that it was better to import our own batch plant to Tonga. And we had a New Zealand concrete consultant come in and design all our mix designs. And as part of the spec, the designers knew that the local aggregates weren't up to great quality as far as durability goes. So there were a lot of additional admixtures added to a mix design to accommodate for that, like the corrosion inhibitors, shrink reducers. They're like so as long as the designers enforce a strict specification, then we can adhere to that.
Richard, I'd just like to add as well, if you don't mind, ocean acidification is something that's also happening with climate change. With CO2 being dissolved into the ocean can actually increase acidity, which affects reefs directly, for example, aragonite, and that's also compounds this sea level overtopping, for example, but also directly can impact on the materials. So thank you.
Thank you, Leanne. Yes, it will. If there is acidification, then the marine concrete is at greater risk. Yes, so more attention is needed there. Now, there's another question. How much time will it take to get approval on design changes in accordance with the site conditions, and how will it impact the scheduled budget on infrastructure delivery? And John, have you got your hand up to answer that? John?
Ning answering.
I don't know whether you're an expert in that area, but underneath it says, John D. You said would like to answer this question.
No, I think I was just hitting the make it go live.
Okay.
We'll put it there answered. We can answer it there.
Perhaps on the matter of we'll might pass that one then. And there's a comment here from Asmi, who tells us that he has an Instagram at beyond.the.tanks, where he has a passion project and spreading awareness on environmental issues and marine life, and he draws that to attention. Someone has commented on, even under net zero pathways, how much sea level rise is already locked in from thermal inertia alone, and is that number communicated to the public, or does... Well, I'll stop there. So for Leanne, under net zero pathways,
even under net zero, we're locked in to they've got projections out to 2130 or to 2300 even. So this thermal expansion and all these has inertia. It doesn't go away the minute we start reducing emissions, which is something that's really difficult to communicate. What we are adding into the environment stays in the environment for 100 years or so. All right, so even if we reverse now, we have what we have. So that makes it all the more urgent to, if you want to mitigate some of these impacts, it's more urgent to potentially mitigate fossil fuel emissions.
Yes, and from what I read, the technology and what would be required to try and remove significant amounts of CO2 or other greenhouse gases from the environment doesn't sound terribly practical. So we're stuck with what we've got. Eldon, I might ask you a question in relation to Kiribati. What about the water supply there, the supply of fresh water, or will Kiribati be obliged to go to desalination?
Oh, good question. So we currently do have desalination plants. They're fully functioning. The challenge we have is the distribution network, the reticulation. There's issues with it where there's a lot of leakages, and we've got to resolve that. So whilst we have two desal plants, two major ones that can service all of South Tarawa. So we are reliant on that at the moment. The current situation with the bore water, I think it's high sulfur in the water. So there is a lot of inconsistencies in the locations of where the aquifers are. And so that's the current situation. We're trying to resolve it by building a new distribution network to go out to the villages.
Many challenges. Yes.
Good times.
Well, look, I think that we've filled our time, and so we will close. Let me just say this, that on upcoming events, which the Hub is organising on the 15th of October, we have a webinar on postgraduate research in humanitarian engineering being conducted at Australian universities, and we actually have 4 universities represented from PhD students on that day, and you'll find that's very interesting, some of the very clever things that they do. That's the 15th of October. We'll be sending a notice to you about that. And in November, I don't think we've quite fixed the date, we will have an important webinar on the application of artificial intelligence to humanitarian engineering. So that will be an important event also. If you are a member of the Hub, or if you are not a member of the Hub, you are invited to join. John will put the link up. The cost is free, and you'll get our publications and invitations. So finally, I believe that we've had the benefit, as Richard Fechner says, of 4 first-class presentations on this very important subject of sea level rise in the Pacific. Our panellists have informed us from the obvious depth of their knowledge that they have gained and generated from their research, particularly in Leanne's case. The Q&A session was enlightening, and I hope that the messages can be put into practice for the overall good. On behalf of the Warren Centre and all of our audience today, I thank the speakers for sharing their expertise and going to the time and trouble of preparing such excellent presentations. So thank you very much to Leanne, Eldon, Scott, and Anthony. And that's it for today. Oh, I should thank John Donna, who is our tech and manager, who puts us, make sure that all of this works. As you heard, we have one speaker in Utah, one in Kiribati, one in PNG, actually. Scott is in PNG, and Leanne here in Australia. So we managed with the wonders of modern science and communications to put everyone together. So thank you indeed, and enjoy the rest of your day.
Thank you, everybody. Thank you to our speakers.